I hope so.
Use Google Photos.
Watch it be cold storage
I
in
don't-
2 minutes. I told you.
This is the one we did yesterday. Akansha?
A hot tub.
And if you need something, let me know. Okay, so this is the one we did at the last, in the last example yesterday. So we're going to go on from here. This is a problem that was just taken straight out of the book. It's not, so there's, as I had mentioned yesterday, equilibrium problems seem like they're pretty friendly to us, but as you'll see, there's lots of different things that, different ways that an equilibrium problem can go. I want you to see lots of scenarios and be ready to be able to do the problems. I'm going to go the whole week this week. This will be the first time all year. I'm not going to nag you one time about doing the homework exercises.
Why?
Not good.
I want you to do all of them though over the break.
I'm confused. What?
Just because we don't have a quiz this week.
my God.
What's our quiz? Oh, it's the week again. Anyway.
Okay. So anyway, let's go on from this. In this problem, we have a k value of 3.75. I like to have the k value right in here next to the chemical equation. It doesn't say Kc, but it means Kc. And it says that all four gases have an initial concentration of 0.8 molarity. So, and then it asks, what are the equilibrium concentrations of all gases? Anytime a question gives you something about the beginning of a reaction, and then it asks you something about equilibrium, then make an ice table. So we're always going to do this. Almost every equilibrium problem is going to have an ice table with it. Maybe every one, not just almost every one. Okay, so initially, 0.8 molarity is the concentration of all four. Now, with these initial concentrations, is it at equilibrium right now?
No. Actually, yeah, it is.
What is equilibrium?
No, it's not.
Maybe.
It's not.
Probably not.
Do we know why?
Because
There's something that tells us for sure it's not at
the
equilibrium.
K exists.
K is 3.75. Remember what K is? It's the ratio of products over reactants.
It has to be one.
Is the products over reactants equal to 3.75?
No.
No, so it's not at equilibrium. I had mentioned yesterday this Q value. Remember me talking about Q? Q is the products over reactants, calculated the same way that K is calculated, but it's not, Q does not have to have everything at equilibrium. You did well. So right now Q is 1, because 0.8 times 0.8 divided by 0.8 times 0.8 is 1. And I will mention too, we have actually written this down the very last day of the thermodynamics chapter. I said, if Q is less than K, that means the reaction shifts to the right. In a reaction as it proceeds, Q is constantly changing. So as we go this way, remember Q is products over reactants. So as the reaction goes to the right, the products are increasing. So as the reaction proceeds to the right, Q is constantly increasing. And as soon as Q becomes K, then everything stops. It just says, okay, reaction says, okay, I'm good. I don't want to be bothered anymore. And it just stops there at equilibrium. So right now, this thing is not. It's still proceeding to the right. And it's going to keep doing that until Q equals 3.75. So we can predict that the reaction is going to shift to the right. Again, because Q is less than K. That means that the reactants are going to go down. They go down by some amount. We're going to figure out what amount they go down. And then as they go down, the products are going to go up.
Sorry, how do you know what
Q is the products over the reactants.
Yeah, so it's one.
Yeah, so Q is 1.
Okay.
And it's less than 3.75, so it's going to keep increasing. Okay, so we have equilibrium concentrations now. It's 0.800 minus x, 0.800 minus x, and then we have 0.800 plus x. Same for that one. The question is, I like to keep that in our focus, what are all these values at equilibrium? So we need all 4 answers at equilibrium. So that means that we're going to need to use the K expression, and it's not terrible to use. The math would be bad, except there's something that kind of gets us out of having to do this scary looking math problem. 0.800, so remember K is products over reactants. 0.800 plus x, there's 2 of those, so it's squared, divided by 0.800 minus x, that's squared as well.
Why is it squared?
Because there's 2 of them, there's that times that. So they're both the same. What do we do with this problem to solve for x? What's that? Take the square root of both sides. Yeah, you see how the right side is perfect square over perfect square? Wow, we can make our math so much easier if we don't do the FOIL method on the top and the bottom and find this quadratic, but just take the square root of both sides. So if I were giving you a problem like this on a test where you couldn't use a calculator, I might do something like this. Where you can take the square, maybe the K value would be 9 or something like that. Take the square root of both sides, you got something that's really easy to work with. So these problems can be done without a calculator if it worked out nicely like that. So I'll just rewrite this thing. 3.7, no, sorry. It's not 3.75. It's the square root of both sides. Square root of 3.75, just from doing it a couple times today, is 1.94. So 1.94 equals 0.800 plus x divided by 0.800 minus x. Now this is something we can easily solve for x with. I'll just give you what the answer is, but if you want to figure it out. Can I say the answer? The x value, at least. The x is not the final answer, but it allows us to find it. X equals 0.255. What's that?
Dang, sometimes it be like that, bro.
Did you guess and check, or did you work it out algebraically?
He did it mathematically using his wonderful mind.
Well, how do you guess and check?
That's your go-to method?
No.
That's hard.
Wait, I didn't guess and check.
Okay, so yeah, you get an x value of 0.255, and now we go ahead and plug it in. The question is, what are all the equilibrium concentrations? I'm just going to go ahead and put the values, so the answers up above each term in the equation. We do have to do the math here. 0.8 minus 0.255 gives us 0.545 molarity for both of these. And then 0.8 plus x for these, 1.055. Okay, so this problem, there was a couple of things to this problem. First of all, knowing which direction the reaction shifted based on what the initial concentrations were. We had both reactants and products, but we see that the Q is less than K, so it has to go that way. The second thing is knowing this quick little shortcut for the math. That made the problem a lot easier. You got a perfect square over perfect square, so you just take the square root of both sides. Okay, gets rid of the x squared terms. Anybody have any questions about anything there? The next problem is the worst one. So we're going to get that out of the way. This one uses the handout. So if you'll grab your handout, go to the very last question in the handout.
The last ones are always hard.
Yeah, save the last one for the hardest one. Consider the reaction, the CO2 plus H2 reaction. In an equilibrium mixture of these gases at 1,000 degrees, the partial pressures are, and so I just went ahead and recorded them. Initially we have that, and that, just copied straight out of the problem.
Right.
Yes?
So for the ice table, you can only use concentration, pressure, or.
That's it.
That's all.
Just concentrations or pressures. Because the only two types of K are Kc for concentration or Kp for pressure. We don't use any other units in the ice table. So it's fine to use pressure. Did you catch though what the problem said about this mixture of gases? What does it say? What does it say about this mixture of the reactants and products? It's an equilibrium mixture. The reaction is at equilibrium with these amounts. So if it's at equilibrium now, we could go ahead and calculate K, couldn't we? And we're going to have to find it eventually, so let's go ahead and just do that. The K value for this, so be aware, if a problem says you have a reaction at equilibrium, or like this says in an equilibrium mixture, you can find the K value. It's probably telling you that so you can find the K. Yeah.
Why is it in the first row then? Why is it not in the last one?
Something's going to happen to the reaction. It's going to get messed with. That's why. So yeah, it could, I mean, you could say, okay, equilibrium is this, but then something's going to change about it, so I just wrote it first. So if we take, and all the coefficients are 1, so this is real simple. That times that divided by that and that. The K value for this thing, this is Kp, by the way, because those are pressures. Kp is 2.00. That doesn't help us right now. It's not even asking us anything yet, so let's keep reading. It says, more water is then injected until until the equilibrium pressure of H2 becomes 10 atmospheres. The problem says, look up here for a second. The problem says more water vapor is added. So the reaction right now is not bothering anybody. It's not doing anything. It's just, okay, I'm doing just fine right the way I am. But unfortunately, the reaction gets messed with. And more water gets added. It throws it out of equilibrium. Now, would you agree the reaction is product heavy? More of a product has been added. So now it's got too much product. What's the reaction going to do? It's going to shift and go that way. Now we know that because look at what the problem clues us into that. It says that more water is injected in, and then the equilibrium pressure of H2, here's the H2, it goes up. So we know that the reaction is shifting to the left. You see that? And when you read about Le Chatelier's principle, it's going to tell you all about that. When you have a reaction in equilibrium, if you add more product, the reaction is going to shift to use some of that added product up. It's going to shift to the left. Or if you add more reactant, it's going to shift to the right to use some of the added reactant up. So in this case, let's go ahead and fill in what we know. I'm going to use a different color for this. Water gets added. The problem doesn't say how much water is added. I'm just going to call it some amount X. Maybe we'll be able to solve for it. The problem also says that the pressure of hydrogen gas goes up to 10 atmospheres. That's all I know from the problem.
Oh.
Yeah?
Since like you know what's going to be added in the change, you can apply the same thing for the CO2.
That's right. That's exactly right. So we all can tell if the hydrogen started at 6.25 and went up to 10, how much did it change by? 3.75. And if the hydrogen went up by 3.75, wouldn't the CO2 also go up? You can't make hydrogen going to the left and not make the other reactant. So if that went up by 3.75, this has to go up by 3.75. Yep. And so we knew what its initial concentration was. We can go ahead and add those together. This equilibrium now is going to be 9.50. So these both go up by 3.75. If that happens, would you agree that the CO is going down by 3.75? When it reacts this way, if we're making the 3.75 of that, it has to be going down by the same amount of that. And so we can find its equilibrium value. That minus that is 13 minus 3 is 10.13 ATM. Okay, now I warned you this is the hard one. I want you to walk through this with me. We all know that this shift happened because more water was added in. But would you agree with this? That even though more water was added in, we don't know how much was added. If it shifted this way and we used up 3.75 atmospheres of this product, wouldn't we also use 3.75 atmospheres of this? So what I'm telling you is this. Two changes happened to the water in this problem. One change was that more water was added. The second change is the reaction shifted and went that way, so some of the water got used up. So I've got both of those changes right there. Some was added, some got used up. So we can actually write in down here what the equilibrium pressure of water is in terms of X. We're stuck. We still don't know what X is yet, how much water was added, but I think we can solve for it. 5.18 plus X minus 3.75. Well, we can take care of the numbers here. That minus that is 1.43, okay, plus X.
Oh, this is.
And the question in the problem. Yeah, I don't know if you did have anything harder than this. It's different when it's not being walked through like this, you know, when you're stuck doing it on your own. But yeah, I mean, I'm trying to show you lots of different scenarios, and this is going to help you when you go to do the problem. So can we solve for X? I think it's pretty easy to solve for X. There's not going to be any X squareds or anything unusual. It's just going to go like this. Kp equals 2.00 equals the products, 10.13, times this quantity, 1.43 plus X, over the reactants, 9.50 and 10.00. Solve for X. And when you get X, don't forget, don't just give the value, you have to add it to 1.43. Would you go ahead and get an answer for it? See if you can navigate your way through the math on this.
This 17.33.
The value for X? Yep.
Maybe that was not flags.
Are we all able to get E for the answer? It's a multiple choice question. You get E?
Yeah, you just add it.
Yeah, so don't forget, if this is a free response, sometimes we get, doing the math and we get a value for X and think, oh good, I'm done with that, move on to the next. Be careful. Remember what the question is asking for. That's why I try to make this deliberate by putting a box around the circle or the term that we need to find. Get X and then add 1.43.
Did you lose like 1 point?
Yeah, it's minor. Yeah. Because of course most of the work is coming up with what X is. Can I answer anything about that problem? How many? Go ahead.
What if two things happen, like H2O and CO and F?
I don't think that we'll do that. Because if two different amounts of if it says the same amount of H2O and CO are added, we'll be able to do it. But if only if different amounts are added, that'll be an X and that'll be a different variable. And I think we only have one equation, so with only one equation, you can only solve for one variable. think that we could do that. There would have to be a relationship between the two. Okay, good question. Yes?
Why would you solve for x if you just like, if you're solving for 1.43 plus x?
Yeah, I guess that's true. You could just call that whole term x, whatever it is at the end. Yeah, and it would be built in. You definitely could do that. Yeah. Yeah, because that's the only thing you don't know when you have the k value. Okay, so now let's see if we can take this one. Hopefully will be easier. I told you that last one was the hardest one. This one I like the problem, but it's dangerous. I'll caution you against overthinking.
You didn't have ice tables though?
Well, let's see. The problem gives us an initial amount of something. It says initially we have 392 torr of this. And then it asks us, what is the equilibrium pressure? So anytime it gives you the beginning and asks you for something in equilibrium, make an ice table. Let's go ahead and do that.
Oh.
Pure AsH3 is placed into an empty sealed flask at a pressure of 392 torr. That's all we know at the beginning. It says something about after the reaction has started, but at the beginning we only have that. Note, what do you see about the first product here, As? It's a solid. We're talking pressures of things. Solids do not exert pressure. So any solids or liquids, just leave them out. No solids or liquids needed.
Wait, what? Really?
Yeah, yeah. K values are only for aqueous things and gases. So at the beginning, the H2 is 0. We don't have any product to start with. Now the reaction says that after 48 hours, which the time doesn't matter, but over time, the reaction happens, and the total pressure in the container changes to 488 torr. It should be obvious what the reaction does. It either stays the same, it turns right, or shifts right, or shifts left. Which is the correct shift?
That's a shift left. Right?
What?
Shift left. Wait, shift. I mean, the equilibrium is going to go up for 48 hours.
48 hours doesn't matter. It just means the reaction happened.
No. I just mean that the reactant.
How? How can they do that?
Because it says after 40 hours, the pressure in the flask is 488.
Okay, the pressure in the flask. Now,
That's one.
in the empty flask went AsH3, but then it can react and go that way. And at the end, you can have some H2 and the. I guess the reason I'm letting you go on, I want you to recognize it can't go left because you don't have anything in the products. Like if I have 0 of that product, it can't shift to the left. I can't make any more of this because I don't have anything to make it with.
Wait, how do you know which way it shifts?
Because if you have 0 of anything, it's always going to shift to make something not 0. Because at equilibrium, you can't have 0 of anything. You follow that? At equilibrium, you'll never have 0 of anything. So it has to shift to the right. And that means that this is going to go. Now, pay attention to this. See how the coefficient is 2 for that, and then it's 3 for that? When I do my minus x and plus x over there in the products, I'm going to use the coefficient so I don't have any fraction coefficient. I mean, it's still going to work. If I call this minus x, that's going to be plus 3 halves x. See that? But I'd rather not. I'm just going to say minus 2x for that and plus 3x for that, just to avoid any fraction coefficients. Fraction coefficients are fine, but I just try to simplify it. Okay? So that means at equilibrium, it's going to be 392 minus 2x for that, and just 3x for that.
Wait, what's the purpose of the after 48 hours pressure in the flask?
It just means that after some time, the reaction happens. That's all. There's nothing about the 48 hours.
So confused.
Okay. Notice in this problem, we never had a K. It never asked us to find K. The pressure in the flask is 488. What is exerting pressure in the flask? This gas and this gas. The total pressure, that's the key right there, the word total. What does total mean? The sum of the pressures, right. You weren't given a K in here because you didn't need it. You only need to know that this plus this equals 488.
Oh.
So there's another type of equilibrium problem where you don't even need the K value. You'll be given a total, not a concentration, you'll be given a total pressure, and so all you have to do is add the two. 392 minus 2x, there's the pressure of ASH3, plus 3x, there's the pressure of H2. Add them together, you're going to get 488.
The answer is 288.
Yeah. You solve for x on this, it's very easy to solve for x, and you get 96. But then, let's see, the question is, what is that number right there? So just multiply the 96 by 3.
288.
Yeah, 288 is the answer. Yes?
There are those really slow reactions that take like 2,400 years.
See, it could be worse. 48 hours, well, that's a drag. You put your reactants together and say, okay, well, I'll write down what time I started this. Come back 2 days later and say, oh, what happened? I'd rather have it happen faster. But maybe I just have a short attention span. Anything else about this? You got one more in you? Can we try one more? I'm going to skip a slide and take you to the last one. Last one has an interesting title. This is not a handout question, it's just right up there.
Physics.
Did the 5% rule in physics?
No, wait, our teacher just told us if something's less than 5%, it's like not significant.
It's negligible.
It's that.
That's what's going to happen with this too.
Oh, really?
Yeah.
Finally,
Yeah.
something Mr. Danek told me was helpful.
I like Mr. Danek.
I do too, but just that sometimes his methods aren't just the best for students.
Ah, okay. All right, so we have a reaction in this one. The K value is given to us. It's a Kc. The K value is small, 1.6 times 10 to the negative fifth. So I'm going to go ahead and write that in here. K equals 1.6 times 10 to the negative fifth. Just like with the delta H, I like to have the chemical equation and the K value right there. And almost as if the K is part of the chemical equation, just because it wraps it all together. Okay, so the question is, what are the concentrations of all species at equilibrium? Looks like we're going to have to make another ice table. That's a molecule, I guess those are both molecules. We could say all molecules. They say species, I don't know. That's the Zoom dolls, we won't argue with them. Ice table. So what do we have? It says, the question is going to be, what are these three values? If 2 moles of NaCl is added to a 2-liter flask. Remember how this is a Kc, which represents the ratio of the concentrations of the products over the reactants? If you see 2 moles, don't just throw 2 moles up here. We don't put moles into the ice table. We either put concentrations, if we're given Kc, or we put pressures if we're given Kp. So they're doing this on purpose. They want to see if you're paying attention. 2 moles over 2 liters is a 1 molarity solution. Not solution, I guess, it's a 1 molarity concentration of NaCl. It doesn't say anything about the product, so we assume that there's 0. So the reaction is going to go to the right, because we can't end with 0 of a product. That's going to happen. Now, keep this. In this problem, we're trying to find what's in the boxes, so we can go ahead and fill out the ice table. This is going to go down by 2x, because the coefficient's of 2. This is going to go up by 2x, because that's coefficient's of 2, and then this just goes up by x. So, at equilibrium, we have 1 minus 2x. Sorry, there's a minus sign. 2x and x. Solve for x, and we'll have our answer. Because every box here has an x term in it. Now this is where the problem could be made much nicer with a shortcut. We'll just say that. Let's take a look at what the math looks like. The k value, k equals 1.6 times 10 to the negative fifth. And that's equal to the products over the reactants. The products are this thing, 2x, squared, because of the 2 coefficient. So we have to take into the two into account twice. Once when we're relating the changes, and then also when you write it in the k expression, you need to use the squared term because of the coefficient. So this is 2x squared, and this is just x. And then the denominator would be the reactants. 1 minus 2x, that quantity squared. Ugh. You want to try to solve that one for x? Cubic. It's going to be a cubic polynomial. Look at the numerator. You got 3 x terms up there. It's going to be x cubed. So we don't have a quadratic formula for cubed things. It would be called the quadratic formula. Quadratic is x squared. But we'd have to plot this thing out and find the 3 roots for it. Or you could do a polynomial root finder, I guess, if you have an app or a program for that. It would be a disaster, a nightmare. In comes the 5% rule. 5% rule is going to be an estimation. As Samir just said, he had heard from a very knowledgeable scientist that he is.
He's a teacher.
He's super smart though.
Yeah, that's true.
Yeah, we're going to make an approximation, and hopefully it's going to be less than 5%, so we can't just neglect something. And here's what it is. I'm going to write the 5% rule out. It's going to be kind of wordy, but I'll show you what I mean by it. Here's the 5% rule. If k is small, which it is in this problem, is 1.6. I'm going to say small means 10 to the negative fifth or smaller.
That's not small.
I'll give that about 10 to the negative fifth or smaller. This is approximate. We're going to have to check at the end and make sure that we couldn't neglect something. We'll get into that too. Then x is small and can be neglected sorry about all the words, when subtracted from slash added to an initial concentration. Just give you a chance if you wanted to write that out. Here's what I'm talking about. If we look back up here, you see how K is really small. A small K means that this reaction heavily favors the reactants, which in other words says that when we start this thing, notice these are both zeros. We don't have any product at all to begin with. When this reaction starts, the 1 molarity is going to start to react, and it's going to produce some products, but when it's just produced a little tiny bit of products, it stops. It just goes a little bit to the right and then stops. What does that mean about the x term? What can you say about x? If it just shifts to the right a little tiny bit, x is small, right? X is going to be a small value. So if I take 1 and subtract off a really small number, what do I get? You get about 1. It's very close to 1. I'll say that again. if I start with 1 and I subtract a really small number, or even 2 times a really small number, what do you get? You get something very close to 1. Is it really 1? No, it's 0.99 something, but it's close to 1. It's an approximation. It's worth doing an approximation versus a nightmare math problem. Would you all agree with that? Can we just estimate our way out of the hard work? Yeah, I'd love to do that. So what that means is this, and this is what I'm saying down here. If x is really small, then you can neglect it when it's being subtracted from an initial concentration. So which it is here. The initial concentration was 1. So I'm going to come up here to my, see how it's 1 minus 2x? That x is small. I'm just going to pretend that minus 2x isn't even there. So now, and by the way, I'll say this also. Notice in the products, the initial amount was 0. So even if x is small, if it was 0 before, any addition to 0 is going to be significant. We can't neglect anything that started at 0. Because even if x is really small, let's say x is 10 to the negative 10th power, that's still infinitely more than 0. So don't neglect anything that starts at 0. Only that starts with an actual initial concentration. So that means this, the numerator has to stay the same. That's 2x and that's x, and we have to keep them. So I'm going to rewrite this thing, and look how easy it is to solve now. The k value is 1.6 times 10 to the negative 5th equals, the numerator stays the same, 2x quantity squared times x over what? 1. It just became 1, 1.0 squared, which is just 1. Now it's way easier to solve this problem than it was that problem with the minus 2x quantity squared in the denominator. Because this, what is the numerator here? Simplify the numerator. It's 2x cubed. Sorry, not 2x, 4x cubed. Because 2 is being squared too. 4x cubed over 1 equals 1.6 times 10 to the negative 5th. Off we go. We'll do that problem. Okay, so if we were to calculate, and I don't know if anybody is calculating right now, but I'll just tell you what the x value is.
Very small. 1.3 times.
No, it's not. No, you did it wrong. It was 4x cubed equals k.
4x. Yeah, I know I did that. Yeah. Took the thing I divided by 4 and yeah, I did do that.
Did you do it by 3?
Oh, I got it. 0.015.
That's better. The 5 rounds up to a 6, I think, doesn't it?
Yeah.
So x ends up being 0.016 molarity. So the 0.016, we're going to pretend that this number right here, look where I'm pointing, this, just call it 1. When I subtract 0.016 times 2 from 1, is it still 1? No, but it's very close to 1. It's 0.9 something. And then this is going to be 0.032. In fact, I'll write it up here. Where? 0.032 molarity. And this is 0.016 molarity. And this I'm just going to call 1.0. There's our answer. Now, we do need to make sure this is only a valid estimation if the x term is less than 5% of what the initial concentration was. You do have to check that because we don't want to estimate too far. So if it's a 5% estimation or less, then it's fine. So I'm going to just add one more thing to the end of this, and that is check to make sure the x that you get is less than 5% of the original concentration. And you'll see when you're looking at the solution guide, and the solution guide uses the 5% rule, at the end they're always going to check. They'll say, okay, the assumption was good. it is within 5%, and so we can go ahead and use that estimation. Now, what is, let's go ahead and do that. We would take the x value, 0.016, divide it by the initial concentration, which was 1. 0.016 divided by 1 is 0.016, and then times 100, because we want a percent here. That's 1.6%. Okay, so that's less than 5%, we're fine. What do you think of that? This is a really nice shortcut. We'll use this a lot when we get to the next 2 chapters. When we're talking about acids and bases, a lot of acids have a K value, equilibrium constant, of very small, like these or smaller numbers, and so we'll be using the 5% rule all the time. And it really shortens our work. It's nice. So don't forget reading quiz tomorrow. You got anything you want to say?
No.
Okay. What about you? You wanted me to, anything you want to say?
Love you, Navneet. You will always be my father.
Oh my God. Oh
Okay.
man, well, that was sweet. Anybody else? You got anything for the,
Mr. Moore, you're like discovering Zeus now. Just on the camera.
I'm not really, the person watching is going to say, yeah, this guy doesn't know what he's doing.